Hi everyone. So I'll be talking about generating code that activates our brains. So this is going to be the tutorial, the actual hands-on part, which again I'll link to towards the end of the slide deck as well, so that we can switch over to it. But before we get there, let me lay out some context on like what I'll be talking about and why this is probably even like an interesting thing to study. So what I shall be talking about is it's a mix of like probably 2-3 years worth of work published at these different places, and it involves a good deal of like understanding about like cognitive neuroscience and like what happens in our brains, and like using math and optimization to sort of control and sort of figure out, help improve our understanding of what really goes on in the brain. So this really is the basis of like what I'll be talking to you about today. So before we, and this is interesting. So when I was like looking for images, apparently Google can generate, not generate, but there are all these images where you just put chapter and the actual number and typewriter, and there seems to be like an infinite number of such images with going from 1 through 100 or something. So yeah, fun fact if you want to put such images in your slide deck. So before, okay, that must be someone online. Okay.
It wasn't me, sorry.
Remove your audio.
Yeah.
Yeah, okay.
I just joined.
You just joined, okay, all right, all right. So before we proceed, let's begin with understanding our brain and just establishing some new bits of information, hopefully, because when I started looking into this space, these are some things that I had absolutely no idea about, just the general organization of like our brain and like how things work. And this was like a revelation for me as I learned. So this was what I'll be talking about was a collaboration between two different departments. One from the brain and cog sciences. There was like an entire team over there which specializes in understanding language, and over at Tufts. So Marina Bears, if someone recognizes that name, she's the founder of, or not founder, but one of the lead investigators in like coming up with Scratch for kids, Scratch Junior. So which is like this toy programming language, drag and drop kind of an interface. So just in terms of understanding programming and like what really happens in the brain, there are like a couple of ways to look at that problem. So you could either like understand it theoretically as to what's really going on. There have been like a bunch of behavioral studies, eye tracking experiments, neuroimaging, and like patient studies. So patient studies is like probably the most interesting one, where you know there are some like defects or like some sort of abnormalities in the brain, and then you look at only those subjects and those patients and then try to understand how their abilities are like affected as a consequence. So imagine someone's language system is completely damaged because of like a tumor in the language system of the brain. Does that really mean they can't program? Can they program? What really, how does that affect it? Again, all these are like problems which we don't really have answers to even as of today. But this is the general flavor of like neuroscience investigations that have happened, at least when it comes to like programming. What I was interested when we started off is just to understand this question of like, is programming language a language? I mean, does the brain treat it as a language, or is it just like a bunch of symbols, and is it more like a mathy, logic-y kind of an operation? And like what's really going on over there? So that was the basis of going down this rabbit hole. And it was like an interesting rabbit hole to say the least, and learned a lot.
So you
yeah.
mean with programming in this context is to have a representation of the brain,
So
like a code?
yeah. So no, not really. This is like literally when I read a piece of program or I'm thinking about programming, what's happening in the brain.
Okay.
That's the perspective. Not really in terms of like abstracting away these kinds of brain behavior as programs, but rather when you literally interact with the program, what's happening in the brain.
Okay.
And thanks. I mean, that's an important clarification, because I think this crowd has both people who look at it both ways.
So maybe you'll get to this later, but programming, it has to be like, is it like in like real programming language? Does it matter, or is it just like structured reason? Like, is there like an overlap, let's say, with like other formal?
Yeah, no,
representations?
great question. So the ones that we studied and some of these past works have actually looked at like formal language or like everyday use languages like Python and like Java and C++ and so on. But there is a much more interesting point, which I'll get to in a bit, which is like just trying to understand it in a more abstract sense, in the sense of like, is control, let's say, the idea of a loop, which keeps getting used in everything from like everyday planning, locomotion, and all these sorts of things. Are those abstractions the same as the abstraction seen in like a program's loop and so on? So those were the set of questions that we wanted to ask as well, because it's not clear. It seems to be the same kinds of operations, but yeah, we weren't quite sure whether it's the same set of abstractions, which I come to it with. Yeah.
Yeah, another question about like the task.
Yeah.
So like I think that our brain can read code in different ways. Like you can have this mode of like I'm now like executing something. I have example and like I'm keeping track of like values of things.
Yeah.
And so on, and
Yeah.
I can
Get
just
a
like
big
look
picture
at
plan.
yeah.
Yeah,
So
yeah.
like, are you focused on like a specific
Model of it. So
yeah.
the interesting thing is there hasn't been like a good enough study just to show what these different perspectives are. It's all anecdotal that we all believe that there are these different ways of like looking at like a big picture understanding of what the larger goals are and like going into like absolute details and understanding what each line in the program is doing. The one that we went after was you are given a piece of program and you're given like 1 minute to just go through it. And then finally, we'll ask you a question about the program. And the question, we were very deliberate. We asked questions about like what the final output would be. So in some sense, you have to do the job of like an interpreter and like get a sense of what's going on. That could still mean that you don't really understand the big picture of it.
Okay.
So I could give you like a prime factorization program, and that has like a bunch of steps. You go through the steps in your head and calculate the final output, but you may still not have that realization that what you did was indeed like just prime factorization. So there is that nuance over there. And I think it's a valid question to sort of see which level of understanding one pertains. I mean, like one would go through when they read this program. But what we were dealing with were fairly simple programs where we would just see, and I'll come to it in a bit as well, where the person would just go through like, okay, this is broadly what the program is doing. The variable names are informative, so I get a sense of what the programs are like trying to achieve. And then I go through that set of operations in my head and like get to like a final answer. So that is comprehension in the way we define it. But it can be defined any which way.
Thanks.
Yeah. So this is some like 101 about like just brain organization, which was fairly startling to me when I first came across it. So what I knew when I started off was like, sure, the brain, there are like specific areas in the brain which are like earmarked for like just say vision processing and audio processing and motor control and so on. But then even within vision, there are subparts within the vision system itself which specialize in like processing faces, colors, places, and so on. So it is that super specialized. So it seems that evolutionarily our brain tends to have, or like these, is the organization of the brain is broken down into like these super specific functions that it is designed for. And this comes up over and again. This is like a very repetitive theme which shows up in like the vision system, the audio system, the motor control system, and so on. And when I call this system, I just mean it's a connected series of like small parts of brain regions, all interconnected through some not necessarily surface level connections, but like some underlying bunch of connections. But they all systematically respond to these kinds of stimuli. So the faces region will not be activated when you're perceiving, let's say, a color or an alphabet or a word or so on. So it is that specialized. So only when you see a face does that one sub-region within the visual system gets activated. So this seems to be the trend even for language. So this is work done over the last, I think, like 10, 12, 13 years, where we know now that there is this language system which can be uniquely identified in almost every person. And it responds both to comprehension and production. So the same system seems to be activated. And when I say activated, it just means more blood is flowing into that brain region. So if you cognitively are involved in certain tasks, the regions involved in those tasks receive more blood. That's how the human system works. And more blood means it is more activated. That's the understanding of like activation. And what we know is this language system or the system of brain regions, it responds to like a bunch of language families. So F. Federico, who's like probably the world's expert on like language and like the brain, her lab, and she's with the brain and cognitive sciences department. Her lab has actually tested, I think, like 50 language families, and this region is uniquely sort of active when it is processing these language families. And what we also know is very importantly, it's causally important for language. So people with aphasia and all these other language sort of anatomical problems in those regions, so if there's like a lesion, if there's a tumor, your physical ability to comprehend language or produce language gets affected. So you know that that brain region is causally involved in like language. So this is what we know about the language system.
Just a question.
Yeah.
For the figure you have there,
Yeah.
the color is where you have more neurons activated? Or
Yeah, exactly. So all the red marks are essentially neurons getting activated. So the language system in your brain may be anatomically different in terms of location than my brain. But what seems to be common is that in every human being, this system exists. And there's a way to identify that system. So it could be at coordinates like 3,4 in yours and like 7,8 in mine, but the fact that it exists and can be repeatedly sort of systematically identified in humans is like the big result. Yeah.
Are there any works trying to inverse?
And when you say inverse,
I mean,
like, what do you mean?
based on these scans, classify which language someone speaks.
So we do that with programs. So this NeurIPS work that is over here, we do exactly that, but with programs saying, can I look at brain activity itself and then try to predict not just which language was being read, but can I determine constituent parts of the program that you read? So just by looking at brain activity, can I say that the program had a loop or like a branch and things like these can be decoded. So it can be done. But I don't remember seeing whether you can go from brain activity to the language itself, like which language family. I'm not too sure.
Because if those reads are accurate, so you're supposed to be able to learn the inverse, right?
Not necessarily, because let's say your first language is like X and my first language is Y. Your response to X is going to be, let's say, high for whatever definition of high. And my first response to Y is going to be as high. So both our brain reads are like extremely high for your language and my language, but they're two different languages altogether. So it's not like a one-to-one function.
I guess it depends on like the variety. Like we see something like constant, like we don't see the
magnitude,
the probabilities here. It's like an average or something.
Exactly. Yeah. But there's only very recent work that's been done on like bilingual people. So like people who are experts in like two languages and then try to get reads out and then use those reads to decode which of the two languages.
And does it generalize also the programming languages? If my first programming language is Python, my mother tongue is like Python.
Sure.
That's true.
Sure.
But what if it was, let's say, I don't know, C?
Yeah, no, that's a great set of questions, and that's what I wanted to answer when I started off this entire like journey, but then realized just like answering it for one programming language itself took me like 2 years. So it's a considerable task just to set this entire thing up. But those are exactly the kinds of questions we need to be asking. What is also not clear is, let's say, does the nature of your, let's say, mother tongue language matter? So let's say your mother tongue language is Python and my mother tongue language is like MATLAB, which are very different in the way in which data is represented and like manipulated. So MATLAB is very matrix heavy and like it's all like visualization, whereas Python need not necessarily be that. It could be more procedural and you could have like scripts. Does that actually make a difference? How does that like end up like getting represented in the brain? Again, all these are open questions. So there's like a hint of work on people trying to study these kinds of questions, but yeah, it's largely understudied. So yeah, no, this is pretty much.
This experiment is in a laboratory, right? So
Yeah.
people are like on the.
So this is all fMRI. So you get yourself pushed into like an MRI machine. If anyone has been in that, it's not fun. For like 2 hours, you're just like lying there listening to like a very loud noise in the background. And then while you're lying there, you're being shown programs and asked to read it. And like you're responding.
Really?
Oh yeah. That's the.
So I have a naive question, right? I'm sure people have come to this, but how then do you disentangle I'm in a very artificial, so like, I'll make some up. How do I not know that these activations are just because I'm in an fMRI machine? Maybe you just have control, I guess.
Yeah, exactly. So the reason why it took 2 years is to just design experiments where you need to be so careful about your design.
I see.
And so deliberate about your design, where you should be able to kind of conclude that the fact that you're seeing the change in experiment condition 1 but not in like condition 2
I see.
simply means that there's a causal variable involved in it.
I see.
So these are essentially like bread and butter exercises of causal sort of experiment design, where you're able to come up with like controlled minimal pairs and then say, because of this, I see activity in one and not in the other, and that should help me conclude that this is stuff that programs cause.
Makes sense.
Sorry, yeah, you seem to have like another question.
I have. I won't say it.
Yeah, we can make this discussion based, and then I can like skip through and like come to the important parts. But yeah.
It's okay.
Okay, we'll wait. Okay. One exception to this behavior that I've just told you, where there seems to be the super specialization, is the multiple demand system. Again, like another name for like a series of like brain regions which are seemingly connected and like seem to come up, show up like quite often. The nice and interesting thing about this is it's not domain specific. Unlike all the domains that I've listed above, it is not activated when, let's say, some super specialized set of stimuli are perceived by us, but rather they seem to be broadly recruited, and I use these verbs interchangeably: recruit, activate, response, etc. So they seem to be recruited in like any new problem solving task. So if I put you in any new context and I ask you to figure things out, where figure things out could mean you just employing some basic set of logic abilities which we as a species seem to be endowed with, that's when this system lights up. That's when this system is activated, which is strange. No one has been able to like characterize what really underlies the constituent like aspects of like such stimuli. But yeah, it seems that broadly math, logic, any new problem solving, puzzles, these kinds of tasks recruit the multiple demand system.
A quick question. Does the vision part also stimulated as you read the code?
As I read code, yes. I mean, so that's because you're just reading characters and like there is some character recognition thing going on. So there is a vision part, but then you could again control it with like getting you to read like any normal text, or getting you to read or getting you to see an image. That gives like a baseline activity for what the vision's sort of activity is in like reading such stimuli. And then you look at the delta. And then you say whether the delta is like statistically significant. If it is, then probably it's the program component that is causing it.
And we have this underlying distribution that it is not shared. Like
It's so this is also work that is being done only now. So there is it's reasonable to assume that let's say I give you like a picture puzzle. So it has an image and you're looking at some tiles or like looking at some crossword or like some maze or something like that. So your vision system is definitely getting engaged. but your multiple demand system will also get engaged in order to solve the specific sub-problem. But what has been shown experimentally is the multiple demand system will never get activated because of just image processing alone.
Okay.
So that's clearly segregated.
Thanks.
Yeah. And that's also been shown for the language system. So language is very distinct, and that's how you design these experiments, where it's very distinct from like general like ability to process, let's say, music or like any such thing where, and the assumption over there is music, math, all these have grammars as well. They have syntax, they have semantics. So if the underlying assumption is that language, the language system cares about all those kinds of stimuli which have structure, which has syntax, semantics, etc., then does the language system also process music? Does it also process math? Does it also process programming languages? That's the real question to go after. And people have done this over the last 10 years, and they found the language system seems to be its own beast, which cares only and only about language. What has not been tried is, and this is called controlled rearing, and it's usually done on animals and unfortunately not on humans, is to get like, let's say, primates and rear them from their birth in a very specialized environment. So imagine having a kid and like teaching and interacting with the kid only in Python from day one. So will that then ensure that will be the true litmus test to sort of concluding that the language system is really not involved in like processing programs? That's
Has that ever been done? Is that ethically?
Unfortunately not.
Well, fortunately, it sounds horrifying.
I mean, I would put my kid through it. I mean, I would love to like.
I would not. I'm sorry. There's a quick question in the chat.
Yeah, thank you. Yeah.
Does that suggest there's universal representation across domains? But maybe they can ask the question so we can get more context. I'm not sure.
Yeah. If you mind unmuting yourself and like probably elaborating a little more, that'd be helpful. But yeah, if you're camera shy, or yeah. Sorry.
Yeah, sure. So I'm not sure if I heard the opposite or correct, but it sounded like you said that there isn't like a specific domain language for, let's say, puzzle solving, reasoning, and those kinds of things. It seems like it's more like the library or like the representation is shared. Is that correct?
No, I wouldn't call it like a shared representation. I would rather say the brain region, which we refer to as the multiple demand system, these blue regions over here, all we know is that seems to be domain agnostic to the extent that it is involved only in like being stimulated by these kinds of logic, broad general purpose logic kinds of tasks. So I wouldn't call this like a shared representation. It's just that this brain region, this system of brain regions, is most excited by or is most activated by this broad class of problem solving attempts. So that's the broad domain. So you can't narrow it down to like, let's say, crossword puzzles or like logic puzzles. It's just broadly logic. So it's the same system that gets activated when you do math, and the same system that gets activated when you play chess and like any other broad logical sort of skills. So that's what I meant when I said it's not really tied down to a specific domain. Hope that clarifies it.
Yeah, that clarifies it. And you mean that is different from the language system, which deals with the syntax and semantics of the
exactly.
Okay.
Exactly. And you would believe, I mean, it would seem strange to you, right? I mean, because like math also has syntax and math also has semantics, and like why should the language system then like be worried only about like music and math? I mean, like, sorry, why shouldn't it also be activated by music and math and all these other similar domains? It just isn't. So that's the whole discussion that I was having, saying the only way to really test that is probably, in fact, it has been tested. So let's say the language system has a tumor, and as a consequence of which those cells just die out. You can still perceive music, you can still do math, you can still like carry on with your life. It's just that your language abilities are completely impeded, which seems to show that at least that brain region is not causally involved in like language, I mean like music processing or math processing. So that's the kind of evidence that we have so far from clinical studies, which makes us believe that, yeah, it's something super specialized and it seems to be only concerned about languages. But like a much stronger test would be like, yeah, rearing kids with like a very specific kind of language and then seeing whether, yeah, this kind of system also latches on to such artificial languages.
I see.
And this is all like work in progress. This is happening as we speak.
Yeah, it's really cool work. Do you think that it might be more about levels of abstraction rather than like seeing it as different like parallel domains? Like maybe the language system is dealing with like the more low level things like the grammar and the syntax. And then like this multiple demand system is dealing with like the high level.
Yeah, no, great set of questions. Unfortunately, no one has an answer. And unfortunately, we don't even know how to define these levels of abstractions that you allude to. That's the hard part. I mean, as soon as you define that question, I think ways to answer it become like easier. But all these are so nebulous in terms of their definitions that it's just so hard to like, yeah, frame the right question saying, what is like an abstraction? What are these levels of abstractions? So yeah, in case you have like good ideas for how to like tightly define these terms, I think you'll be onto something, and like this community would like greatly benefit from it. So yeah, unfortunately, we don't have a good answer for that.
I see.
So an idea. Like I think that, as you said, like when you read code, you can say, okay, this loop does that. But let's say in natural language, so sometimes we read words as just like by how they look.
Right.
You don't actually read every character. And what if you present the words with spaces?
So there's been, the whole field of psycholinguistics for the last, I think 40 years has tried out these things. And they've tried to really figure out like what it is that makes something difficult to comprehend, easy to comprehend, and so on. And there are some theories around like what's the best sort of thing. I think the most validated one and replicated one that I am aware of has to do with surprisal and these other kinds of statistical properties, saying our brain at the end of the day is a statistical machine where it's trying to make some inferences. And what we see as easy, hard, completely depends on our set of priors. So if we have good priors, we make immediate sense of it. If we don't, we don't. That's really the best understanding of like how these things work. But thanks. I agree, that's the line of attack that I would also employ. And it goes back to something that Jose mentioned in his talk as well. So these kinds of closed tasks are like beautiful for cognitive neuroscience efforts. So closed tasks, for those who are not aware, are like you hide out certain things and then see what like the participant responds. So that kind of gives you a sense of what their priors are and like what they expect. And that will reveal whether, if I have like a large piece of text and I blank out, let's say 75% of it, can I still understand what's going on? Can I still like perceive like what the larger meaning is? If yes, then that gives us like a clue about like what are these signals that we are picking up and like what's helping form that narrative in our head. So yeah, I mean, there's an entire field that is dedicated to this, and like I'll be doing it gross injustice if I try to like summarize that field in like 2 minutes. But yeah, that's broadly what you should be. How do tonal languages work? So I'm not really sure what tonal languages are, but let's come back to this. I mean, I think there's like a fair amount of ground to cover, and we're already 30 minutes past. So yeah, let's park this for now, but I'll come back to Hugo's question on like tonal languages. All right, so moving on. Yeah, these were the two brain regions that I broadly highlighted, the language system and the multiple demand system. This is like an average brain. The language system is usually on your left. For those who are right-handed, it's usually on your left side. And the multiple demand system is like also on the left side, left and center. That's broadly the way to understand it. And the question is like, what really is happening when we understand code? And I've set the context up now as to why we are interested in like understanding which brain system is involved in code. So these are the steps that I would imagine is involved in code comprehension largely. So the vision system is activated, as we discussed. I mean, you're reading like a bunch of characters. You recognize those characters and you form like a sense of tokens and statements in your mind. And then broadly through some iterative process, you keep staring at those tokens and you get a sense of what it is doing. And then finally, if you have to trace it or you have to debug it, you have to find like the value of a particular variable, you will kind of dry run it in your head and sort of do steps 2, 3, 4 probably in some mixed order iteratively. So this is broadly what I call understanding code, and what I specifically call code reading is not when the vision system is activated, but steps 2, 3, and 4. That's broadly code reading. And I differentiate and introduce this term called code comprehension, which is specific in this context. When I say, okay, steps 2 and 3 is really what we care about. I mean, that's the comprehension part. So it could be like big picture planning, detailed planning, whatever. I don't really care about it. But as long as it's different from like actually mentally tracing and debugging, like dry running the code in your mind, that's fair game. I would call that code comprehension. So, and this is code simulation, this fourth part. So what we would assume from the spiel that I've just given you is that this fourth step, in whatever order that it actually occurs when we read code, should likely engage the multiple demand system, because this is what the multiple demand system is really good at. I mean, you or like is known for. So you mentally tracing something, debugging something. So the multiple demand system will very likely be activated in this step for sure. What's unclear is what's going on in these steps and how do you experimentally isolate them. That's the harder set of questions. And which is what we went ahead and studied, and we set up these careful experiments to make sure that these two weren't conflated and were easily separable and so on. And just to give you a sense, and I've already alluded to this, that was Jose's question as well. So that's what an MRI machine looks like. fMRI is again functional magnetic resonance, where you're in this machine, there's a magnet that's spinning around you at certain frequencies. And really what the magnet is trying to capture is rate of change of blood flow in your brain for some least count of like time step. So it samples, I think, let's say the least count is probably in the order of like 1 second. So rate of change of blood flow in like every second in your brain is what is getting computed or calculated or stored. So the best way to set these experiments up, and it's all relative. So if I'm like particularly active or my brain is like wired in some way, I could be attracting 5 milliliters of blood, whereas someone else could be attracting 3 milliliters of blood. And that blood could still mean that 5 milliliters could still mean the same output, the same computational output performed by the brain as compared to the other person. So these absolute numbers don't just make any sense. And that's why it usually comes down to the experimenter to go ahead and set these experiments up so that they have some comparative baselines to sort of conclude what's really happening in the brain. So yeah.
So we talked about like where there's a stimulation and like we saw a heat map, but I'm curious about like the amounts. Absolute amounts, okay, maybe not, but are there things that are like, is it true that if you're like thinking harder, you see like more stimulation and like
for sure.
Vice versa?
For sure, yeah. The resting state is usually considered to be the baseline, which is some amount of blood, which is like routinely getting pumped. But as soon as I get you to do some challenging task, you clearly see like an increase in blood activation. And that's really what we rely on.
So what are the most demanding tasks that we are familiar with?
So it depends. So for the multiple demand system, any task really, I mean like any new task. So if I ask you to disassemble this phone, it's completely new, you're trying to figure things out. So that will be like the 4th of July in your brain. It's like fireworks. But for like vision, even just seeing the face passively is enough to create like a blood spike relative to what the vision system is generally used to. So it depends on the stimulus. All right, so this is the general strategy to carry out fMRI experiments. And these are the two systems that we ended up studying. And these are the two languages that we ended up studying. And the reason why we include Scratch or Scratch Junior is because unlike Python, it has no English in it. There's absolutely no words in it. So it becomes like, again, like a natural control to subtract the effect of words in like how these brain systems are getting activated. And what we found was the language system is not consistently activated. So that was like a big result. Yeah.
So quick question, the Python code, does it have comments in it?
No, it does not have.
Okay, so it's just pure like.
It's pure
okay,
code. Yeah,
cool.
it's pure Python code. But one interesting condition that we controlled for is we completely switched out variable names with like Japanese like words.
Okay.
And we made sure that people who were like participants in the study did not know Japanese, so it was pretty much gibberish for them.
Okay.
And we saw that it didn't really make a difference.
Okay.
Yeah. So code variable names do seem to have an effect in terms of like really sort of big picture understanding, but when I ask you to focus and comprehend and ask you questions about it, then the brain, at least the effect of like variable names just seem to diminish. So it is good for general maintenance and like general understanding, but when I'm testing you and you're like focusing, it doesn't like the effect doesn't show.
Interesting.
So yeah, what we found from this entire study was, the language system not that activated, but the multiple demand system, it is. So it comes up consistently in both Scratch and like Python. And when I say multiple demand system, this is the multiple demand system when I've subtracted out the effect of just manually tracing each line and like trying to figure out what the output is. So this is the story about like code and brain and like what's happening in our brains when we read code. There's another set of results which I probably won't have time to get into, which connects to, I'm not sure who asked this, but slightly more like an abstraction saying, are there, if the multiple demand system, if we know that it is involved in general logic like tasks, then can I define logic in terms of like constituent primitives that come up in a programming language? Because every logic task in some sense can be described as a program. So programs are like a natural way to describe any logical task. And does that mean the multiple demand system then has all these finer primitives inside it, which helps express these ideas? And we have some initial evidence on that as well. And the answer is yes, it seems that there is something going on over there, but a lot more work needs to be done. Anyway, so that's the story about our brain. And let's switch gears to just trying to understand this perspective of goal-based generation, and code modification. And again, tying this back to the entire like topic of this talk, the reason why goal-based is important over here is because we'll finally come to, and the exercise also relates to it, we'll finally come to the part where we will try to understand what is the best way in which we can modify code or generate code, which let's say drives the activation in the multiple demand system. So if the hypothesis is that loops seem to activate the multiple demand system more than variables, can I discover this fact just by generating code automatically, which drives the activity in the multiple demand system? So then you can look at the generated code and see what code was generated. And if you find loops come up more often, then very likely that loops do play a big role in driving the multiple demand system. So that's where we want to head to. And I'm setting up all this brickwork so that we can like go ahead and answer that question. So the way to understand goal-based like generation or modification, this is again joint work with folks over at the MIT IBM lab and like Tamara, who's I think she's working with you, Alex.
She was working.
Was?
She's
Yeah.
an Eng in Saman's lab.
She's an Eng now in Saman's lab. Yeah. So she's also been involved in this space for a while now. So broadly, let's try to understand this from the application of like adversarial examples as like a goal, and that can be generalized to any sort of goal. But in this case, in this context, let's look at adversarial examples and like modifying code adversarially to achieve certain goals. So I wouldn't call this state of the art. This was state of the art like a couple of years ago, but these were the broad applications. And the general way in which these kinds of, I'm sorry, I didn't even complete my sentence. So these were the broad applications in which machine learning played like, or had started to show interesting results for like software engineering tasks. So there were around the 2000, let's say 17 to 20, or like probably 15 to 20, 2015 to 2018, 2019, before the whole GPT sort of thing came in and codex stuff came in. There were models that were being trained to go after these specific kinds of tasks. So I think one of the older ones was code auto-completion, has always been a task that has been on like that has been like addressed by this community. Improving variable names. So this JS Nice was like a 2014 work, which kind of set the whole thing rolling. Assignment grading, error fixing. I think Jose's talk exactly like deals with this. Vulnerability detection, predicting types. These are the kinds of applications which machine learning seem to play a role. It's still unclear like how significant a role it can play. But at least what we know now is like, yeah, code auto-completion for sure. There's like some studies which show that, yeah, it does like improve productivity, but others are sketchy. It's still work in progress. We're still trying to figure out like what's the best sort of application space to use all these models. But this was the beginning, and these are the kinds of models that were getting trained. And these were, unlike the GPT style, these were very application-specific models. So you would see typically one paper release one model for vulnerability, one paper doing one model for variable names, and so on. And typically the way these models are trained is you have a program and you choose like a representation. You either like describe them as tokens or like ASTs or graphs or like whatever. And you have an encoder which builds on those representation. So the encoder's job is to, just consume these tokens and form some, distributed representation of like what those tokens most likely mean in some space. And you use that distributed representation for some downstream task. So it could be vulnerability detection, predicting types, whatever. This is the general flow. And what I mean by model is, the encoder and the representation it emits is like the model in this case. And the real question that has bothered me for like a while, or like at least puzzles me even now, is like, what is this distributed representation? I mean, like, what information does it contain? And can I, like, with just defining like a vector which is of like size 512, encapsulate everything, all the nuances that are going on in a program, and like get it to like encapsulate just that particular information that I'm interested in? It's still unclear. I mean, we're not really sure how these models learn, but that's something that we wanted to investigate. And one way of investigating this, and these are like examples of how these models can be tricked. So tab 9, something that we've been talking about. It's a module or an extension, like a package that you can install in Vim. I don't know, it must be supporting multiple other interfaces now. But when you have this in Vim, you can fool it by having code context in such a way that the top recommended suggestion, the completion suggestion by tab 9, is a library which actually has a vulnerability in it. So you can write code in such a way such that when you hit tab 9 gets confused and actually recommends like an incorrect library instead of like a correct library. So in a normal case, mode_cbc is never used because it's deprecated now. It has known vulnerabilities. Nobody uses it. And very likely any auto-completion system would like probably that be low in the suggestion list. But just the fact that you can surround the context in certain way can completely fool these models. Suggests that probably these representations are brittle in the sense of like the context that they can capture and so on. So this is what we really wanted to study when we started off this line of work. And we studied this in the context of program summarization because it was probably the most used application, and yeah, you push in a code, the model tries to summarize in like a sentence what that code is doing. And yeah, VS Code had already integrated this by 2019, and there was like a lot of work that had happened around it, a lot of data sets and stuff. So what we wanted to then do was we wanted to understand if it was possible to change a program in careful, controlled ways, which would ensure that the prediction would completely flip. And when I say careful, controlled ways, I mean that semantically, I don't want to change the meaning of the program. I want to just make minor cosmetic sort of modifications, and those modifications should end up effective enough that it completely fools the model into predicting something totally different. So that was a task that this work focuses on. And this is more so to take a step back. The goal here is to trick the model. That's the goal-oriented modification or the goal-oriented code generation that I was talking about. So yeah, this is essentially the problem which I just described. And just to give people some context, if you haven't seen these kinds of problems before, this is like very popular work in vision, where the adversarial examples sort of work, where you've got like a panda, a classifier that says panda with 60% confidence, and then you add some random Gaussian noise to it. So adding that Gaussian noise makes sure that the image is changed imperceptibly to a human. So for us, the third image still looks like a panda, but the machine is completely fooled by it, and the classification is like given with like almost 100%. So the question then is, how do you sort of learn this noise in like a systematic way? So yeah, the objective is it looks similar to humans, but different to the model. But with programs, what is the kind of noise that we can add? And how do we even define this? How do we formulate this problem? Because it should look similar to a human, need not be the same. It should be exactly the same to a compiler. If there's a compiler in the loop and the compiler tries to execute this program, it should semantically be exactly the same. But the model should like perceive it completely differently. That's the aim, that's the objective. And yeah, we can skip past these slides. One such modification is just changing variable names. So easiest to fool, because these models, unlike the brain, unlike the comment that I made about like the activity that the response system in the brain, that it doesn't really care for language, like variable names. These models do care for these variable names. So the models seem to be extremely sensitive to what variable name is used, and usually for most of these models, it's enough to change like a couple of variable names to some adversarial names, and that will completely flip the model's decision. That's how brittle, at least code summarizers, are. I'm not sure what the state of the art is, but yeah, at least it was 2-3 years ago. So yeah, you've got like these bunch of candidates which you can either replace. So you can replace variable names. You've got multiple variable names to replace. You can change arguments. You can add in like dummy print statements, really. If you believe that it is part of your threat model, that adding like a print statement doesn't really affect the semantics of your program. If that is fine, you can add these print statements. You can add some dead code. So even the most like state-of-the-art dead code removal sort of SAT solver kind of like technology usually fails to detect this as like dead code. So this, we know that a sign of anything cannot be less than -1, but like a SAT solver really, or like any kind of like dead code removal technology, really finds it hard to reason about these kinds of like math properties and will unlikely be able to remove these.
What if it's -infinity?
Sure, I mean, it'll still probably remain the same. I'm not sure. -infinity could be, it depends on how like carefully engineered these dead code removal systems are.
I think it should be like a -infinity.
You think it'll make it harder?
No, okay, never mind.
No, I want to understand like.
I think that like, because like it is a programming language, so it has some like, specifically Python is like, what if it is, okay, never mind, and I'll check it.
Sure, yeah, no. I mean, the reason why I bring this up is like, it is the justification for this is it's a valid program transformation where the semantics will still remain the same because that if condition will never get executed. But if you have like a dead code remover in the loop, it is very unlikely going to remove that dead code for you. So it's a valid program transformation in that sense, where you can actually insert that dead code and it's perfectly fine for the compiler or like the checker. So you can add like a dummy try catch. You can like unroll a loop like a bunch of times and make some minor modifications over there. So all these essentially are transformations which we can introduce as humans, which will not semantically change the program, but can possibly fool a model. And these kinds of transformations, Jose also mentioned in his talk, he had like a whole suite of like replace operations and insert operations to repair programs. These are replace, insert kind of operations to fool program models. So that's the difference in perspective over here. So, but there is a problem. There's like a much more fundamental problem of how to even solve this problem. So let's say you buy this argument for a minute and then say, okay, this is fine. You can actually go ahead and like transform things this way. The real question is like, how do you go ahead and actually implement such a transformation routine? So let's say you've got two variable names to choose from, and how do you actually go ahead and like see which variable name actually goes ahead and fools the model? You would do something fairly greedy, saying, okay, let me pick the first variable name. Then if I have a vocabulary, I'll go through this vocabulary, make replacements. So go through each token in the vocabulary, go ahead and swap it out with that X, then push it into the model, see what the inference is. If the decision has changed, great. That means we have found like what is a good replacement option. If it is not, try something else. So you replace that with a candidate, you check which has like a better loss or like which degrades the performance more, and then you pick a winning site and a winning replacement. That's the greedy brute force way of doing it. So what this seems to suggest is like, if you've got a vocabulary of tokens, which is, these tokens over here, token Q seems to, and if you replace Y with token Q, the model gets fooled into believing this program is doing, or is this program tries to open a file instead of saying hello world, something of that sort. The problem is, this is combinatorially, it's a pain in the neck because let's say you've got like 4 choices and you've got to make 2 replacements. It's clearly like an exponential problem. And the question then is like, how do you even tackle this? So I won't get into like how we go ahead and tackle it, but rather this big picture of just understanding that there are 2 subproblems within this. One subproblem is the site selection problem, where you need to simply figure out which of these 2 or which of these 4 possible sites should I go ahead and like perturb and like transform. And once you fix a site, what transformation should you apply on that site? Those are the 2 big problems that need to be solved. And of course, if you solve one of them, both of them efficiently, you're already making progress instead of doing it randomly. So that's the broad perspective of like just trying to understand these goal-driven edits and goal-driven generation. This is like a small part I'd like to focus on because this is what really the hands-on tutorial ends up implementing. And if you paid attention to Jose's conversation on like program repair, I'm pretty sure you can reuse ideas over here into program repair as well. So what we're trying to understand is like, how do you implement this site perturbation algorithm? So how can we improve like a greedy strategy where we know we have like a vocabulary of tokens to pick from, and we want to, let's say we fix 2 sites, these are the 2 sites. What is the best way such that I don't have to do like a greedy walk and replace each token onto it, but is there like a better way to go ahead and realize what those tokens are, which can be replaced onto those sites? So that's what we're trying to really understand in this. For those who haven't seen this kind of a representation before, this is like a one-hot representation, a very bad cartoon for like a one-hot representation, but you should imagine that these are vectors of length, the vocabulary in your, the number of words in your vocabulary. So let's say your vocabulary has 20 words, 20 different tokens. So the length of this each vector is going to be 20, and the fixed index corresponding to this token, let's say def, is going to be 1, and the rest are going to be 0. So that's just like a categorical representation of like just representing information in like a set or a category or like some discrete set. So let's say you've got this one-hot representation for some function, some snippet of code that you're interested in modifying. Here's like a perspective and this usually helps me like understand things like fairly quickly on like how to think about this problem. So in a typical setting, I would push this program represented in this particular way into, let's say, a code model like CodeBERT or CodeT5 or any of these kinds of language models. They generate a representation, distributed vector, which is like a condensed form of all this information. And you use that for your downstream task to, let's say, predict the type or like a vulnerability or like whatever. So there's that downstream task over there. When you train these weights, when you train the weights of CodeBERT and when you train these weights of this, let's call this like a mapping model. This could be like a feed-forward network. It could be any simple sort of connection which goes from this vector to your downstream task. When you're training the weights, this is fixed, the input is fixed, the output is fixed, and the weights are being learned. That's your typical like 101 supervised learning sort of setup. So essentially you're calculating the derivative of the loss with respect to each weight, and you're moving in the direction where this derivative is minimizing. So that's how you train these weights, and that's how you learn these weights, both in this model and let's say in the mapping model as well. So this is the regular training perspective. What happens in code generation is, or like adversarial generation, or call it whatever, let's call this just like goal-driven generation, is you flip the picture around. So you say the weights are fixed. I'm not going to really touch the weights. The downstream sort of task or the downstream label is fixed, but now I want to change the input. So that's really what we're doing. So it's the same gradient descent machinery. It's the same backpropagation machinery. It's just that instead of like having the input and the output fixed, now we have the output and the weights fixed, and we want to find out what input like changes, what changes to the input will ensure that my output behaves in a certain way. That's really what we're trying to do. And you can define any loss function over here. So let's say you initially predicted like panda. Now you want instead to predict gibbons according to the image that we just saw, the example that we just saw. Now you can define a loss saying my y pred, or the predicted y, should be as close as possible to gibbons and not pandas. So that could be my new loss that I'm defining. So this would have been, crap, I switched the slides order around, but let's say I had like a little question mark over here where I was going to ask you, if you didn't really observe, what this derivative would be with respect to. So remember, we're trying to find changes in the input, which will lead to a specific output, which will lead to the output loss being minimized. Because in the gradient descent case, we saw that the derivative was with respect to the weights of these models. What would the derivative be with respect to in this case? In the case that we're like modifying, let's say we want to find changes to the input. And I kind of reveal it. I mean, it's you just take the derivative with respect to the input over here instead of the weights, and that will give you changes made to the input, which can lead you to whatever weight that you want. So there are like a couple of tricky parts, and that's what the implementation really focuses on. How do you propagate? And if you've dealt with backpropagation before, you will know that this one hot vector, there's usually like an embedding layer somewhere over here, which takes this one hot vector representation and like maps it to like some continuous representation. And that's not differentiable. You can't like propagate gradients all the way back to your input itself. And what's the workaround to that? And that's how most of these Huggingface models also implement stuff, which we'll see in the implementation. But that withstanding, I mean, like, let's ignore that for a second, and let's say that we can actually propagate gradients all the way back. What we are then trying to do is, let's say def, this token def was at like location 1 and the rest was 0. what you're going to do is now move in the direction of this derivative. And let's say these derivative values are something like this. I've just made these values up. So now when you move this, move in this direction, the new values are going to be -2 plus 0.4, yada, 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 plus 0.7. Now there's like a new token in your vocabulary, which seems to be weighted much more than your original token def, which then suggests that the new modified token that you're really looking for, which will maximize your goal, would be the token corresponding to, let's say, the argmax, the max sort of value in this particular vector instead of the previous one. So that's how you end up like coming up with like, let's say, like a new token over here, saying you started off with the code snippet def foo blah blah blah, and now you have something which is totally different called return foo blah blah blah, which now optimizes for whatever goal that you have. So in the context of this entire exercise, this is what I mean by like generating stuff. Of course, this can be applied to like an actual decoder, and you can like do constraint decoding in exactly the same way, and nothing really changes conceptually. But in our case, we start off with like a random program, and then we tune it and we modify it, and we want to modify it to an extent where you now get the desired goal out of that particular downstream model. So this is the big picture on like program modification, program generation. This should very well also be applicable to code repair, I'm pretty sure, in like different flavors, because essentially what we are then trying to do is like modify like a buggy snippet of code or buggy line of code, and you want to change it until, let's say, the language model predicts something whose gap is like low, or like some distance metric is like optimized or something of that sort. So the same kind of formulation will work in like program repair as well. So yeah.
So I'm just curious about like we are training something. Like we're training the representation, like the first layer, or like before the first layer, the input.
Yeah.
But we can also think of like doing like spend the same computation budget on just training one layer in the middle of the model or somewhere.
Sure.
Or just train the model.
Sure.
So I'm just trying to understand like what are the benefits of having this better input representation.
So your question, if I understand it right, is just like a clarification. I think it's clear to you, but probably someone else. There's no real training involved in any of this, at least in this modification step. And I'll get to your question in a bit. Just as a clarification, this isn't training in the regular sense where we are training all these billions of parameters over here, but rather over here, it's just like trying to figure out values for each of these one hot like vectors over here, and they're much smaller. They're in the orders of tens or thousands instead of like the orders of billions. So this process is like fairly simple and like straightforward. Answering your question of like input representations and like why it even makes sense, and correct me if this is my understanding of your question, and correct me if I'm wrong. If I understand it right, you're saying you can either have like this large model where you have all these parameters and it forms some input representation, or you can have like a narrow slice of it, just like a couple of layers of it, which seem to do the same task, or which seem to, and you train it from scratch and it seems to like do as good a job in representing the input. Is that right?
Practically, I mean, like why not just fine tune the last two layers or something like that instead of learning the inputs?
But it depends on the use case. So here's the thing. So we'll see in the fMRI use case especially. So your question is like, why do you even have to bother with like modifying the code, like the input itself, when if you have a goal, you can just directly fine tune on it and like train the model, like let's say last two layers or like last layer directly on the goal itself. It depends on the problem statement. My task over here is not to improve this model, but rather use this model to discover new information. So let's say I have this code summarizer which summarizes programs. And let's say the code summarizer like GPT or Codex or something like that has been trained on correct programs. which comes up with like correct summaries of programs. And let's say it's ideal, it's like perfect, like 100% accuracy, 100% recall. Now, if you give me such a model, and if you give me an incorrect program, I'm now relying on the knowledge already encoded in these models to discover what is the best way to modify the given program such that it starts behaving correctly. So it's not really, my goal is not really to, I want to be able to explain or discover information in the token space as to what changes I need to make so that it starts behaving correctly rather than improving the model itself.
Okay.
So I wouldn't quite know how to solve this problem just by fine-tuning the last two layers.
Okay, I think it's an open question.
I see, sure. Jose,
Yeah, I have a question. So maybe we'll talk about this, right? But so I can totally imagine, you change the input so that, what used to be, a good summary is now a bad summary.
Right.
It used to be a good function is now a vulnerable function, whatever.
Yeah.
Is there any notion though of like incorporating an objective for like the naturalness of the replacement?
Great, yep, it is. So you can introduce, that's the beauty of these kinds of, so this loss, not this loss, this loss synthesis over here can be, it can be decomposed into multiple components where, let's say, the core objective of flipping the model's accuracy or flipping the model's decision is just one component. But you can define, and I've seen this happen in like very few instances, the naturalness can be computationally described as saying, whatever token that I do introduce, its probability given the surrounding context needs to be extremely high. So the bag of words probability of that newly introduced token needs to be maximized as well. So that's a shared objective that I can like latch on to this synthesis loss. So it will be, the first term will be fool the objective, fool the mean. The first objective would be fool the model's decision, plus some alpha times making sure that the bag of word probability of that particular token that gets discovered is also, the likelihood is maximal. Plus, it's not a reserved word. So it'll be quite silly if I bring in like a new token that gets replaced with like, let's say, a keyword or something of that sort, which you don't want to do. So all these kinds of constraints can be naturally strung into this kind of like a synthesis loss. And I've seen it happen in natural language processing in like constraint decoding work, but I haven't really seen it.
So I guess the part I'm still trying to understand, so I understand
Right.
I imagine doing this, but like, how is this different? It sounds like we're kind of like re-implementing a weirdo decoder.
It exactly is pretty much the same. So I would rather, instead of calling it like goal-driven generation, I would simply say this is constraint decoding. And this is one style of constraint decoding.
Okay.
You could, but the technology to add these different loss functions, instead of, it then comes down to like which layer you want to apply to. So whether you want to apply directly to the input, you could do the same thing on the embedding space as well. Instead of going back all the way till the input, you could do it in the immediate embedding space, or like in some papers, you could do it in the decoder's representation itself, which is exactly, it goes down to the literature of constraint decoding. The only reason for doing it in the token space is that now you have explicit control on the vocabulary. So you can really say like what words to pick from, what vocabulary to choose from, and so on, which you don't really have the benefit of if you're like adding those constraints somewhere in the decoder step over here. And then it's more of a trial and error.
But so, okay, but so in this case, you can't do something like byte pair encoding for the tokens or anything, or can you?
These are all on the byte pair. This one hot encoding that I talk about is after the initial tokenization step.
Okay.
Yeah. So that we'll see that in the code exercise as well.
Okay.
So
there's a question in this.
Yeah. Has there been any work on implementing two separate networks, one for program prediction and a symbolic model for learning the vocabulary and grammar and its effects? No. So that's something that we also talk about in our paper, saying probably the kind of information that we have learned about how the brain behaves is like motivation enough to try out different architectures and like try to resemble what's going on in the brain. But all that's like wishy-washy. I mean, there's no real evidence that like you mimicking how the brain works should actually improve like prediction capabilities and like downstream performance and so on. But yeah, it's an interesting idea. I've seen works which kind of incorporate all the neurosymbolic stuff. So you should probably chat with like Omar or like Alex. All the neurosymbolic stuff usually has some ways to incorporate these kinds of statistical properties as well as like grammars and like symbolic stuff. So I know Swarat has like some some recent work where they incorporate grammars in like language model stuff and so on. How about curriculum learning? Yeah, I've seen some flavors of that as well. So yeah, it's all fair game. Yeah.
So arithmetically, the first thing we do with this one-hot encoding is we multiply it by a matrix.
Correct.
So we can also treat of it like having a dictionary.
Yep, So there's like an embedding matrix which is multiplied with the input. Yep.
So like if we want to have like we have a model and it has fixed architecture.
Yep.
But we want to enlarge the dictionary.
Yep.
So we have to use a dictionary.
Absolutely. Yep.
The alphabet. So basically in that case, we'll have to, instead of learn like different, like an alternative to one-hot encoding, the first layer, which is equivalent because it's linear.
Correct. Okay. That's the way to think about it. Yeah.
Okay.
So you can make these tweaks at any layer, and it again comes down to like what the problem statement is, like which level you want to intervene and so on. But that's broadly the idea. Yeah. And it all comes down to like choice of vocabulary and like whether you want to add new words and like how you want to deal with them and so on. So then in those cases you will move down the layers instead of like doing everything. Yeah. So that's, if you've understood this, and this algorithm over here is essentially exactly what I described. So it's got the whole site selection problem and the site perturbation problem. The site perturbation is what I've described. I won't go through this algorithm in detail. We'll probably go through the code itself, which kind of like relates to what's going on over here. So this kind of ties both the pieces together, like brain, what's happening in the brain, and like this kind of like code generation method that I just spoke to you about. And this is again joint work with like a collaborator, a grad student over at the Brain and Cog Sciences team, where we've been trying to understand the language system of the brain and trying out these kinds of ideas in the language system, but the same applies to programming languages as well. And what's happening in the brain when it comes to understanding code. So the way to understand and like build this kind of a system is there shouldn't be any surprises now, that you really need to learn like this kind of like a mapping model. So let's say the full picture is something like this. So you've got a program and you want to understand like how people's brain activity is when they read this piece of program. So you actually get people into a scanner, get them to read this. You do it over like 20, 25 people, and you get like some sense of like, okay, what the activity is, brain activity is. Then in order to be able to run this kind of like a modifier, you would need information to sort of propagate, some gradients to propagate from this brain signal all the way back to the inputs over here. And the way you do that is you learn a mapping model first on like a bunch of people. So essentially you're trying to map the representation of, let's say, CodeBERT or any of these language models onto actual brain values, brain representations. You learn this on like, let's say, 100 to 200 people, extremely expensive process. And then for some unseen set, for some unseen like program altogether, you can then use this mapping model as like an in silico way of like running these experiments.
So you may have explained this, but I had to step up.
Yeah.
what does your widespread look like here? Are they actually like time series, or is it just you have like category, like you discretize the space? and
Yeah,
say
yeah,
here,
no.
this
So
brain or that?
it's I think that itself is like a tutorial all by itself of like what's the best way to represent that. But I think the short answer over there is it is a time series. You learn a regression, you learn like a generalized linear model on that time series, and you use the weights of that linearized models as proxies for like activation. So it's a vector of numbers where those numbers essentially are weights fit to a time series. That's the technical way of like how this community learns like brain activation. So
Okay, and you could, let's say, if you decide to take some like sequence model, fit it to that, and then use some like hidden layer and say this is now my representation. That would be fine too, instead of like just a linear model.
that would be fine too. People have tried it and they weirdly and surprisingly find like these linear models to correlate the best somehow. So that's like a whole cottage industry in itself on like what's the best way to represent like fMRI data.
I see.
But yeah, for the purposes of our experiments and like generally, yeah, it's essentially some model which is fitting a time series and like it's the weights of those models.
Okay, and do people like share these? Like, is it kind of like?
Public? Yeah.
Yeah, like now I'm saying like the next set of people don't have to run these.
Oh yeah, that's the whole purpose of like like putting out running these experiments. It's ridiculously expensive. I mean, I think MIT's rates, I'm not sure, and I'm not sure a 1 hour scan. So each person requires at least like 2 hours of scanning, probably not in one sitting, but probably across sitting. One session costs somewhere like around like $2,000 or something like that. It's like ridiculously expensive.
Okay.
So all their like imaging budget, I mean like all the PI's budgets in like neuroscience essentially goes out on these kinds of things. So it's an order of magnitude worse than, let's say, CS folks who probably the only compute is the only expense, but even that's not getting any cheaper these days. So yeah, we are all like in the same boat, I guess, in some weird way. So yeah, so the goal is to learn these mapping models. Once you have these mapping models, you're in business.
Okay.
Then once you've learned this mapping model, which tries to predict, let's say, a code representation from CodeBERT or any language model onto this widespread, then you can use gradients and propagate it and do all that sort of good stuff and like start changing stuff and see what actually maximizes this prediction. So the nice part about this kind of a setup is you don't have to guess. You don't have to come up with like 20,000 candidates for what your hypothesis is of like what activates like a particular brain region, but rather use this mapping model to do your experiments offline, come up with like a set of candidates which do maximize this prediction according to this model, and then get like 5 people or 10 people and then show them those new modified programs and then verify whether that actually does show increased activity.
So I had a quick question too. So is it that harder tasks require more activation, or is that the way it typically works?
Not really. So it depends on like the brain region. It depends on like a bunch of factors, but the way you should interpret like more activity is that it is definitely more involved in processing that bit of information. So the vision system, for example, and this is the example that I gave, just by passively looking at a face or a cup will light up compared to its normal activity. It's like abnormally high. Just by passively just like seeing the face region like goes off. Whereas if you're doing something like puzzle solving, the multiple demand system then shows like a kind of like a linear trend. Like the harder the task, the more involved the multiple demand system is. Okay. So very different brain behaviors and depending on the region, but the ones that at least for language that we're trying to find out is the inherent difficulty in like reading a sentence does not really correspond to activity in the language system, but clearly there seems to be something more and we don't know what that is. We don't really have a good hypothesis of what that is. And these kinds of experiments make it really convenient to study what is really going on. And yeah, what we have found, in fact, for the language system, which is a completely different set of experiments, is that the generated stuff looks very weird and strange, but even those strange things end up like, not all strange things end up lighting up or activating the language system, but there seem to be some subclass of strange words which seem to get the language system excited. So yeah, this is the broad setup, and essentially, yeah, the tutorial just walks through like the rough layout of like how you would build this kind of a system to maximize predictions and like for like some particular downstream task. So in this case, the downstream task is brain activations. In the tutorial, I play a trick on you and I don't really add any neural data or anything of that sort. It's a simple like code defect detection task or something. Essentially, this mapping model is like a classifier. That's all I really want to demonstrate. That if you have a classifier and if you have got a language model, how do you then trick the classifier into predicting whatever you want? So it could very well be like a learned linear model or like learned model, which learns to predict these brain activations, and the code will look exactly the same. It's just that these weights will look different.
I have a question. So for the like input rewrites changes that you did in your paper, like what are the extent of the like? Is it kind of like you might have a for loop becoming, you know, some functional map, or
could be. So it completely is the designer's choice, and that's where the experimental questions come into the picture, because all those are in some sense experimental biases that we are introducing. So at least in the case of neuroscience, you would want to let go of like all inhibitions and then say, let's do this hypothesis free and see what comes up. That said, there's always in these kinds of setups, there's always the question of, is the artifact that is getting generated in the input, is that a consequence of this model being poorly trained or like poorly capturing the underlying representation, or is it just that the behavior indeed depends on these kinds of quirky kind of like modifications to the input? That's an unresolvable question unless you have like 100% accuracy on this, but that's the gray area that this entire experimental setup relies on. But that said, to answering your specific question, in the tutorial, I mean, I do the same thing. I put a limit of like 5 tokens being replaced somewhere in the program. This magic number 5 seems to, we seem to share this magic number.
Do people in these fMRI, do they ever use like a collection of different code embedders, like, you know, toss it through Codebreak, multi-pattern code? Okay.
Yeah. So the
to kind of mitigate that issue. Maybe.
Exactly. So the neuroscience paper that I spoke of, so we went through like the whole laundry list of like code models out there, and yeah, this paper essentially we go through like I think like 15 models or 10 models.
Okay, but like as separate experiments or combined? Like, is there any value to just like combining all?
Oh no, we didn't really combine stuff. We were like going through them separately. Actually.
Got it. Okay.
Yeah, we didn't really combine anything. Yeah.
So I'm interested in tokenizing programming languages, and like I'm collaborating with a group that is currently training large language models. Like specifically, there's the Centacoder, which like it has these funny tokens, and also other models. Not natural. And I'm just curious, and Alex and I also talked about that, like if a more natural tokenization can help. And actually, Alex told me about like there's one try that like there was been a try with spaces or tabs or something like that. Like add a token for that, which helped. But I'm just curious, it's an open question, but maybe you have like some input on like whether if you tokenize the code in a more natural way, if it can help in downstream tasks, let's say code generation. And
I'm not really sure.
So I know I'm not the person being asked, but in the Flame paper for domain-specific stuff, that's like a core idea.
Oh, really?
That if you tokenize the right way for the language you're.
Oh, this is what you mentioned. Okay.
It helps for performance. Like, I don't know if that would work for other things.
so also you had the privilege of like, since you like, it was like 60 million parameters.
Yeah.
So you had the privilege of like doing it from scratch. But let's say you want to use like one of the
Yeah, like how do you reuse the tokenization? Yeah, so we have this project. We haven't worked on it very much recently, unfortunately. But the idea is you have exactly what you're saying. It's basically you have a pre-trained model with some kind of generic vocabulary. Could you, recompress or split or whatever you want, re-optimize the tokenization in some way that would work by kind of sending it through one mapping first and then operating there. I think it's interesting, but we have not done more. But I think that the answer is yes.
Yeah, all right. So unlike Jose's tutorial, I didn't really intend this to be like a standalone document. So if you missed out on like most of the talk, this might seem like Greek and Latin. My apologies. I mean, this is just me being bad with the amount of documentation. I do mention like a big picture. So if you've just tuned in, hopefully this big picture will make sense, but it's why I'm very unlikely. I mean, we went through like a good amount of information for all of this to make sense. So let's see, let's get started. So 3.8.10. So I remember it being 3.8.11, but let's see. That shouldn't make a difference. So this is just like regular setup stuff. None of this should be interesting. It's just like, yeah, maintenance stuff. Let's see, the file system is here, so that is important. So probably the three most important files, four rather, are the notebook itself, the notebook as a Python script, for in case you don't want to run the notebook, because that's how I developed this. I developed it as a script and then I had to copy it over to a notebook. There are a bunch of things in utils which we use. So in fact, one important thing is, let's get it to open. And I believe you can make a tab of it. Okay, good. So that's one. Let's see. Let me talk through each of these. Custom bird gradients. All right. Let me also do this so that it looks bigger. Too big. Okay. Alrighty. So these are the four probably most important files: the notebook itself, utils.py, custom-bird.py, and gradients.py. Gradients has this one method, getGradient, which I'll talk about in a bit. Custom-bird has some modifications to the regular bird implementation that is shipped with Huggingface, and I'll again talk about like why we need this. This may not be the best way to do it, but for simplicity's sake, and just to make things like easier to convey and understand, I've just copied over Bird's code from Huggingface and made some modifications to it, and we'll see what those modifications are. Utils has some regular run-of-the-mill kind of utils, but I think probably the slightly more important one, or the slightly more useful one, is this one, get most sensitive sites. And again, I'll talk about like what's really going on here. All right, let's chug along. Boring. Okay, so this is the data set that I'm going to be demonstrating this whole thing on. And again, I have completely fooled you in to believing that you will actually work with neuro data. You are not, unfortunately, going to work with any neural data over here in this tutorial, but rather this code base is to get you to wrap your head around like how you would implement this if you were to like deal with neuro data or like any other data. So this is more general, where this is the architecture that you would probably need to appreciate and which we'll use to sort of implement. So there's like a language model which produces representations. There's a mapping model which uses those representations to get to some downstream prediction. And then we want to now change this downstream prediction by making changes to this input. That's broadly what this entire tutorial is all about. So in the comments and the text over here, this downstream model is called, I refer to it as theta map, theta being the weights of the model. This is called theta LLM, large language model, no creativity points over there. Yeah, the data set that I specifically deal with is from the code XGLUE data set. So this is the one which in fact is on defect detection. So defect detection over here it has been trained on some vulnerability data set, and it essentially is a binary classification task where 1 means there is some insecure code, 0 means it's most likely secure. How well the models learn and how well this task is learnable, I have my apprehensions. It's not like a straightforward task to say whether like a piece of code is secure beyond just looking at like keywords and beyond just looking at like library calls. But anyway, I mean, this is just for demonstration. So for our purposes, this should suffice. They have like a rather pain-free way to like access this data set. So I'll just go ahead and do that. So get data set. So these are again a certain number of constraints, similar to what Jose described when he was talking about his work. So I put a cap on the number of tokens or like how long a program is, just because for the specific model that we deal with, code BERT in this case, it just accepts like 512 as the max token length. So I want to stay well within that range. And I don't run this for more than like one example. So I'm just running it on one example. So there's no batching, there's not like a clean sanitized production grade piece of program, but rather just runs it on like a couple of examples just to show how things work. All right, so this is the easy stuff, and this is where we define this function called optimize. And optimize really, what it's doing is it's taking as inputs a program to transform, which is the input program which you want to modify. It accepts a model, so you could pass it really any model. It could be like CodeBird in this case, or it could be Codify. I mean, pick your favorite model. You need to provide a tokenizer corresponding to that model, a configuration corresponding to that model, and a loss function. So this loss function corresponds to the loss function that we described over here, which is the synthesis or the generation loss function. So this loss function in the case of like a binary classification task is just going to be a cross entropy loss. So if it predicts 0, you want the cross entropy loss to instead now predict 1. If it is 1, you want to predict 0. So if the original prediction for a program, let's say the input seed program, whatever this random program is, initially predicted 0, I want to now make modifications to it such that it now predicts 1. That's the goal. So this is analogous to the brain task where, yeah, for any given program, if you have the brain response to be X, you want it to be Y, and you can like clearly define what these X, Ys are. This is the desired target. So in the case of our current task, 0 becomes a 1, 1 becomes 0. So the desired target completely dependent on, it can be independent. I can like make sure that irrespective of what the original prediction of this program is, the desired target is always like 1 or 0 or whatever. In the case of brain responses, we usually have like a range of like what this brain activity numbers are, and they're usually z-scores because you normalize it and you do like a bunch of jugglery with it. So you can set some value saying, according to the data that we've seen, high activity corresponds to this value being close to +2 or +2.5 or something like that. So, and then you try to like move or modify your code such that it hits that magic number of 2 or 2.5. Device, results route, all these are like, yeah, like PyTorch stuff. I mean, where you want your results to be dumped, or CPU, GPU, the number of iterations. So this is, you can like, because this is like an iterative stochastic gradient descent kind of like an algorithm, you can define the number of iterations you want to run this optimization routine for. You have its own, it has its own learning rate. the number of sites is the thing that we were talking about a while ago. So Jose used this magic thing of like 5 transformations or modifications. I use 1, in fact, so you can like change that to 5, you can change that to 100. You can like go crazy with that. Multinomial samples is something that I didn't speak to you about. I can like briefly talk about it, but I won't get into the details of it. It's essentially, think of it's the argmax step, and I'll come to it. Like how do we take an argmax, because it's not really differentiable, because we need to go from continuous to discrete in at some point. And this multinomial sampling just helps with like going from that continuous to discrete, making that switch. Sample info is just like information about, like, just for logging purposes, information about the program that is being transformed. So if there is like a particular index in the training file or test file or whatever, I just pass that info into it. Verbose is like whether you want verbose info or not. So I'll walk through this code in a bit, but that just defines the function. It doesn't return anything bad coding practice, I suppose, but I just dump it out to like files. So each code is going into a CSV, and you can open the CSV and read like what the original program was the modified program, what the modified program's output was, and so on. So all those things are getting dumped into some CSV. I've also annotated, loosely annotated, steps in this algorithm and their correspondence to like what appears in this actual codified algorithm. So pretty much the implementation follows this pretty strictly, besides these little facts where you're doing this per index and then you do it for the entire string and stuff like that. I can go into the details, but whatever. I mean, it shouldn't be a leap of faith for you to first read this algorithm and then look at the code, and then you should be able to see like a correspondence of like what's really going on. Better me would have probably named the variables also exactly the same, but I don't think that's happening right now. But yeah, whatever. This is where we do our modifications to Huggingface's APIs that Huggingface exposes. And again, I'll talk in like a short bit as to why these modifications need to be made in the first place. And this is essentially the main method which calls everything. So let's try to run this. So it's actually loading the custom model, or like our wrapper on like a Huggingface CodeBert model. This could be the result of like why there's like some funky performance, but I'm yet to get to the bottom of it. Okay, this is like a sample program from the dataset. So not the most readable, its formatting is slightly screwed up, but essentially, according to the dataset, this is like a it is like a safe program. It's got no issues apparently in it. And I don't know, to be honest, but the hope is that we can modify multiple sites or like multiple tokens in this program for it to result in something where the target changes from 0 to 1. So that's the intention. And these are like parameters. You could run it for like a bunch of iterations. So what was happening when I checked this last was the loss was not improving. So there's something going on, something funky going on. I'm not really sure what that is, but let's run it anyway and see what's going on. So this does run the entire thing, and you'll see what I mean when I say the loss isn't improving and like things are not working the way they're supposed to. Oh, I don't know. Okay. So you'll see that this is like a weird sample because this is the log likelihood for the 0th class. This is the log likelihood for the class 1. And the sample really sits somewhere in the middle. The classifier doesn't seem to do a good job, or like is not super confident of like either class. It thinks it's probably class 0 more than class 1, but the margin is not too much. So yeah, this will take a bit because I think I gave it some crazy numbers, but I should have just given it like smaller numbers to begin with, just to show how this works. Oh well, let's see. Let's make this number of sides to be 1, number of this to be 1, number of iterations to be 10. Learning rate is probably all right. Yeah, let's see. All right, let's see what happens over here. Okay, all right. So it's dumping out. Yeah, so this is what I was talking. The loss doesn't really improve much. So there's something clearly going on, and I should either the number of iterations are too few, or the step size is too big, or like there's something going on. So I need to carefully understand what's going on. But the big picture will remain the same. And this is like, it comes down to hyperparameter tuning and like trying to figure out what's the best way to get this to work. But let's quickly understand like what's going on behind all this code. So for those of you who have used Huggingface models, this should remain. This should be relatively unsurprising. I mean, you just load a sequence classification model. So this fully trained, like fine-tuned model essentially has both this and this component in it. I could have picked a model which did only this and then added weights myself, but I didn't want to because when you have like a fine-tuned model, it just makes things more convenient. This is where I do the custom stuff. And what I'm doing over here in this particular line is just initializing it. But over here, I copy over the weights of from the original fine-tuned model onto the customized model, and I do some extra steps over here. And what those extra steps really are is essentially to circumvent this whole embedding layer, which is non-differentiable. So I define my own embedding layer over here called embedding version 2, which is like a linear layer, which is of size, like dimensions, vocabulary size into the embedding dimension. So given any input, this linear layer essentially maps the input, the one-hot encoded input, into like whatever like embedding dimensions that the embedding layer generates. The problem is, in like a regular model, I am not at the liberty to do this because the embedding layer over here in between is not differentiable. It takes like an input ID or a token ID and converts that token ID internally, and PyTorch doesn't really expose that API details to us. And it just converts it internally to this, it's a lookup essentially, it's a dictionary lookup, where it converts the input token ID into its corresponding embedding. And we want the gradients to propagate through that embedding back to the token layer. And as a consequence, this hack where we define our own linear layer, we copy over the weights of the embedding layer, the layer that has already been trained, because we don't want to generate any new weights over here. We just want to just use the same embedding layer, but use it as like a PyTorch linear layer instead of like a embedding layer. That's the only difference. So you just copy over the weights as is. And those are the lines that you see over here. So you just update the weights, and you need to update like a series of weights because this sequence classification class is like a larger class which has like many subclasses, and you just need to recursively apply this weight copying. So that's the significance of having this custom bird class, where the modification really is in this one hot. So if you look at one hot, or if you search grep for one hot, those are the changes that I have done. I mean, essentially, that's pretty much the only change to the existing API. Once we're done with that, we can like focus our energy on like the optimize method. So let's see what's going on with the, oh, it's already run. Oh, it's already run this. So let's see, what did it generate? So it generated, did it change? No, so okay, so here's the thing. This is a case of like a bad example where the gradient method is not able to optimize it, and it's most likely a hyperparameter issue where it's just not able to find the right sort of surface to be able to push this loss down further. And do I do like a, yeah. So yeah, there's something minor going off, and I could probably come back to this and like set it up offline and like share the updated code base. But yeah, this is typically how it works. What you would generally see is this loss goes down, the prediction from like one class will start shifting to the other class. And it's like super straightforward with like sentences and other kinds of things. It should be straightforward with this as well. And I strongly suspect some hyperparameters going wrong. And yeah, when it comes to the generated code itself, I don't know whether anything has changed or not. One way to do that is, let's just check the diff of like the generated code and the original code. So this was the original program. And let's just check the diff. Oh, there has been some, so it has managed to introduce this word called interference, which is very strange. So interference seems to be some keyword that the downstream model must have learned as like something which maximizes the loss, but this could just be noise as well. So these are the kinds of edits that you'll see. Currently, I've not constrained it to seem natural, as Zaid pointed out, or like I've not really done any extra sort of things to it. The loss function is fairly simple. It's just the cross entropy loss. I should add like a can be extended note over here, where you can really add like a bunch of other components to this loss function. What's happening in the optimize step, which is probably where all the action is taking place, is as follows. So yeah, you have this iteration loop. Here's where you do the softmax step. So essentially any one hot representation vector, which is zeros and ones. So let me go back to this particular slide. Yeah, so we want this vector, which is essentially a continuous vector, to look discrete. So the way we do this is you model this as like a multinomial distribution, where the distribution is like, you believe that this is some probability distribution with these as your weights. So you can think of like, this is like, you can like flip a coin, and these are the probabilities of each of those coins to show heads. And then from this, you want to sample one draw, and that draw will tell you which of these is most likely going to be 1 and which of them is going to be 0. And yeah, because this is like a multinomial sample thing, you can actually like specify the fact that you want to draw just like one of these numbers need to be 1 and the rest need to be 0, which is essentially taking like an argmax of some sort, but you're not doing like a strict argmax. This is like a softer version of argmax for those of you who have dealt with argmaxes. And that's what's really happening in this step over here. So there's like a softmax happening over here. Once you do it, you can do this like a bunch of times. You can sample, you can do the multinomial sampling like a bunch of times and take like some winner of that voting process.
Another question. So
yeah,
there was some like location importance thing. Are you doing this for every token in the input?
No. You're right. So where was the location? Yeah. So the location. So this is get most sensitive sites is essentially a workaround to solving the site selection problem. So if we recall, we had these two problems: site selection, site perturbation. Site selection is which of these locations should I go ahead and transform, and what is the transformation that I need to do at that particular location. we don't really solve the site selection problem, but that can also be cast as like an optimization problem, and you can pick up like those sites optimally, and that's what the ITO work was all about. But here, what we just show is you can just do like a gradient-based sort of one backprop from the model and see which of these tokens has the most effect on the loss, and then just sort it in like descending order.
Okay.
And then pick the top K sites from that sorted order. That's essentially it. So get most sensitive sites, does the sorting, and what I do is there should be like a loop somewhere which goes around let's see, where's the loop which, yeah, so if token to attack, let's find this. Oh, I'm not on GitHub. Yeah, so token to attack. Yeah, so if token index is in token to attack, then I sample it, otherwise it won't. That's the way to go about it. So yeah, so the multinomial sampling happens, the softmax, it's like a standard step. From there on, you just calculate the gradients with respect to the soft input. Over here in step 17, you get the gradients and like whatever, some extra information from it. Then you see if the loss that you achieved on this perturbed token, or like this new token, the softmaxed token that you have picked up, whether that improves the direction, whether that improves the loss landscape. If it does, you pick this token, otherwise you reject it. I mean, if the loss is better than the best loss that you have seen so far, then you say that, yeah, this is like a good sample, I keep that sample and I move ahead. So I do the same thing over and again across like multiple iterations. And this is the step where I do the gradient descent step essentially. So if you go back to step 18, this is the standard SGD step, U equals U minus some learning rate times the nabla, the gradient information. So that's what's happening over here in line 18. And there's a torch multiplication with the learning rate and the gradient that we got it, the gradient that we saw, and we do it with the tokens that we'd like to perturb. The rest of the tokens, you just leave it as it is. And as a consequence, you get like another new input, and then you make a softmax of it, and then go through the same process again. So that's really it. The other thing is like this file where you actually calculate the gradients with respect to this new loss function. That's a bit of like an implementation trick. So you need to be able to appreciate how to add hooks to PyTorch, so that PyTorch modules, so that you can like sniff gradients that pass through your modules. So that's really what I'm doing over here. There's like an output hook and a gradient hook that I define, and the embedding layer, whatever the embedding layer that I have defined, I just like calculate the gradients that pass through it. And that's really it. You do like a lost of backward, you find what your embedding layers sort of gradients were, which you were interested in. And the fact that this is calculating it is because of the hook, and you enable the hook, you can calculate these gradients. And once you do this, you just return what the gradient was and what the embedding is. So yeah, if you're seeing all this for the first time, it could be intimidating, but this is more not like there's nothing new in this in terms of like technology, or like there's nothing new in terms of like the science of doing this. It's just that implementing it can be slightly tricky, and being able to navigate your way through PyTorch and like PyTorch's idiosyncrasies and the facilities that they provide in order to achieve these kinds of goals is a bit of a learning curve, but once you get used to it, you get used to it. So
can you connect this notebook with any of the slides you showed before, kind of like the like for the pipeline?
Yeah, sure.
It's very abstracted here, right? So.
Oh yeah. So okay. Yeah, fair. And that's what I was hoping to do with yeah. So let's see. Let me start with, in fact, the optimized step is essentially the only, so let's start with the model itself. So this custom BERT sequence classification model is really this stuff. So this entire box of, let's say, this map model and the language model, this corresponds to the custom BERT for sequence classification model. So essentially what we're trying to do is like modify this. The weights of these model, this entire model is fixed. Using these fixed weights, we're trying to like modify these inputs. The way you modify these inputs comes from here. So you have this program, you pass this program. So let's say the desired target is whatever the label is, the inverse of it. And this is the sample code that we really need to modify. Let's say we start with that. So C is this, T is whatever prediction is, it's complete opposite. So if it was 0, you want to make it predict 1. If it is 1, you want to predict 0. The way you tokenize this and the way you get this one-hot encoding is through a utility function, which should be somewhere around over here. So this really is the function which does pretty much implements this entire flow over here. So let's try to find where this one-hot is. So one-hot is where we get this representation for each program that we pass into the system. And its implementation should be in utils. So there should be like a convert to one-hot, which is like a 2-3 line program, which does this convert to one-hot. Once you have this one-hot, then it's a matter of like implementing this gradient descent algorithm, which I just described. So this site sensitive, like site selection stuff pertains to, yeah, just picking the one that I just described to Jose. I mean, which is just like, yeah, you've got a bunch of candidate sites in the program to pick from, and you just see which the gradient with respect to each of these sites, and you sort them. And the sites which are most sensitive to the output, you just pick those first to go ahead and make your perturbations. So in essence, this could be some site like, let's say, def. So it could just be this particular, the first token among these 5 tokens. So this will come back and tell you that, yeah, the first token, you should probably go change the first token, then the 8th token, then the 10th token, and so on. So that's what the tokens to attack really is telling us. Once we have this, we run the optimization process, which I didn't fully describe even over here. So the optimization process really is this process over here, where you take this program, push it into this model, run this through your custom loss function, pass the gradients back all the way back to the input, and then do a softmax and like iterate with respect to this gradient update rule, which is like standard like gradient descent stuff. So that entire thing happens over here. So you start with the number of iterations, you sample like a couple of times, then you pass this to a model, you call a model somewhere over here, I would believe. Input one hot is already coming from a model somewhere. So yeah, this get grad step 7, like yeah, line 17 of the algorithm. This is essentially running this entire loop where it passes it, pushes it into these models, predicts it based on the loss function, it gets back gradients. So this entire thing is happening in this one line of code. And then based on what you get back from this routine, you get to then pick whether the modification that you just made, was it like a useful one or like it didn't really improve the gradients anyway. If it did improve the gradient, then you pick that, you hold on to that particular modification or transformation, and then you just go ahead with the next token. So that really is what's happening in this slightly dense function, which I'll probably break up further and like definitely add more comments. But yeah, big picture, that's what's really going on. So I gave a very hand wavy sort of notion of like how this step works of taking gradients with respect to inputs. That is described in painful detail in this code, which yeah, I don't think I'll go through it line by line, but essentially that's what's going on over here. And I'll yeah, if someone has like doubts or like you go back and like read through it and it doesn't make any sense, let me know, but I'll also do my best because this is going to be used by some folks in my lab as well for some other tasks that they're interested in. So it's in my interest to definitely pepper this with enough comments so that people actually get to use this and like understand this. But yeah, those were the big pieces when it comes to the implementation of this idea. And again, this is just a prototypical like kind of like an idea where this could be the downstream task need not necessarily be a classification 0-1 kind of a task where 0 says it's a non-buggy code, 1 says it's a buggy code. It could just be brain data. It could be like anything that you can imagine. So one interesting application is in coming up with like careful experimental stimuli. So all these experiments, neuroscience experiments, rely on like carefully constructed stimuli where you are able to control them in like very careful ways so that causally you have some sense of like the rate of change of brain activity. You can like causally link it back to what caused, like what was responsible for it. And this kind of like a setup can help you automate that process instead of having to hand construct those kinds of stimuli in like over like, I don't know, 2 weeks, 3 weeks. So it just helps you do it in like one shot over like a couple of hours. And you can control, you can exercise like a great deal of control by defining whatever loss function that works best for you. So yeah, I mean, that was like pretty much what I had in terms of like how this works. We can play around with it a little more, but let me know if there were
So
any
can this
questions.
be reused for some other folks here or Zoom? Or-
Yeah. I mean, I have used this in like 3-4 different applications. So adversarial, like just model explanation is like one immediate use case. Like just if someone gives you like tomorrow, someone comes and says, okay, this is code T6, which does better than code T5. And because it does great on like commons and like execution traces as well. You could use this kind of like a framework to probe whether the inputs like essentially what you want to see, what this kind of like a setup helps establish is like some sort of like a sensitivity analysis. So how much can like a delta in the input, how much will it affect the output is essentially what this kind of a setup helps you really understand. So someone comes up with like a code T6, you can really do these kinds of careful sensitivity analyses by making little changes to the input, little deltas to the input and seeing whether the output really is affected by it or not. So yeah, it's got like a broad set of applications. I have a friend in electrical engineering who painfully comes up with like electric motor designs by hand, where he has like a certain set of constraints in his mind, and he's trying to satisfy all these constraints by coming up with these designs. And these kinds of tools are like also like, again, optimal to discover those optimal sort of designs which would satisfy certain goals. The only trick is the entire thing needs to be differentiable end to end. But even if it's not, you can use like black box optimization and you can use like a bunch of other tricks to get it to work. So yeah, I imagine at least that's the case that we make as well, that this can be applied in like a broad field of like broad space of like engineering / like neuro / like code kind of problems. So yeah, fairly generic way to think about like how do you change an input so that your response to that input changes in like a controlled way.
So I'm also not very familiarized with the language model. So what happens is that you import the transformer thing, and then you make a call to some server, or you have like the actual model here?
Oh, so this is everything is over here. So when I do like a pip install, so the requirements file should have transformers over here. So this just downloads all the transformer models onto your local instance. And what I then do is make modifications to that transformer model by adding in like my own embedding layer to it. And the way I call that is by overriding the Huggingface model. So these are the BERT Huggingface models, and I just create a wrapper around it. So I just say, yeah, create my own model and then copy all the weights from this model onto my model, and then just use my model for the rest of the tasks. So yeah, everything is local over here. There are no API calls, so you can fully run this locally if someone wants to run this. Yeah. Yeah, there's no codecs.
So it's just like a freeze thing, right? Just get the weights of the model.
Yeah, exactly. So you just need weights. So even if someone says they've trained like a linear regression model, all I need is that matrix. Once you give me the matrix, that's all I really care for. Because once you have a matrix, you can set that matrix up in PyTorch, and then PyTorch allows gradients to propagate through it. So then you don't even need a language model. You don't need all these intermediate sort of models. You just need weight matrices, and you just need those weight matrices to transform an input to an output. And as long as you have that connection, you can start modifying the input to produce whatever output that you want.
More questions? Yeah.
So I have a question. Have you ever thought about using this for like non-adversarial purposes? Like for example, you could imagine that you're actually trying to optimize like some criterion that you have. If you could somehow formalize a loss that captured like
Absolutely. Yep.
how fast is this code,
Yeah.
you could optimize.
Yeah. Exactly. I mean, the beauty is that this is super flexible and comes down to the designer's choice of like a loss function and a vocabulary. And the right combination of these two can yield like very interesting applications. So one non-adversarial sort of setting that we showed, I mean, we used this was in fact to show brain reactions and brain responses and so on.
Right.
Because it's so hard to describe and pin down like theoretical like underpinnings of like how that response shifts and describe those responses, that we just learn a model around it and then plug this sort of framework in and then like see what sentences respond to or like produce certain kinds of responses.
Right.
So that's a natural use case, but if you can define a loss function for something, you can pretty much use this. That's pretty much what it comes down to. So that goes back to Jose's point as well, saying how do I then ensure that the modified programs are actually natural and like more like these aren't like stupid like modifications like this one like word being added over here at the end, which doesn't even make sense. You can control for those things as long as you can describe those constraints as a loss function.
Mm-hmm.
So once you have that, you're in business. Yeah.
Cool.
Yeah. So yeah, most papers I read in synthesis, I'm usually in my head, I'm doing this translation where I'm like, oh, okay, this is like an idea which can be translated. If you define like a loss function to this, then you can pretty much describe it as like a generation task. So which I think that idea is caught on now, and there are like a bunch of works which kind of make use of that idea in different flavors and shapes and forms. But the crux of it is essentially that. Yeah. So I think we're well. I think it was till 4, right, originally. Yeah. So we are well ahead of time. If someone wants to play around with the notebook or something, feel free, and yeah, I'm happy to like step through and see what's going on.
Anyone on Zoom have questions? Okay. Ask.
Yeah, any questions from Zoom or for folks who are on Zoom?
I have a question. This code is very cool. Could you please like give us an example of how you could use this to make those like causal tests that you were talking about if you want to make like an experiment?
Yeah. So sure. So the causal tests to set a causal test kind of thing up over here, let's try to define the causal test to begin with. So the causal test could be, do code models, do these language models rely on variable names? So that's like a simple test, right? So let's say your code model tries to generate, tries to autocomplete some stuff. So given like a partial snippet of code, you're trying to autocomplete stuff by prompting, let's say GPT or like any of these models. And you have a hypothesis that variable names make a difference. So that's what you really want to test. So the way you would set this up is you will say that the sites that you want to perturb, so the site selection problem over here would be all those sites which are just variables in a program. So you won't go ahead and perturb any site at random, but rather given a program, you are just concerned about variables that you want to go ahead and perturb. And there are like simple Python libraries which will help you construct the syntax tree of a program and then help you identify which are variables in those in that program, instead of you having to write like a regex or like any grep kind of like a thing. So the syntax tree will give you free of cost where all the variables are. Once you have that, all you can do, all you would want to do over there is go ahead and like perturb just those sites. And when I say perturb, I mean this particular line over here, which does like a softmax in step 18 of the algorithm. You're doing it not on all the sites. So you'll see this is currently happening on tokens to attack, but rather this would end up being variable names, tokes, which are variables. Pardon my like bad variable naming, but these are essentially only those tokens which are variable names. So you want to apply this optimization procedure only on those tokens which are variable names. And what this will end up doing is, and you will define a loss saying the autocompletion that you get from the model should be an incorrect autocompletion or like a correct autocompletion, whatever. So let's think through the hypothesis of like variables not having an effect. So if the variables, let's say the variables have an effect, that's your hypothesis, that's the null hypothesis. So if the variables do have an effect, and if you change the variable names, then you should see that, you should hope that the model is not able to come up with like an autocompletion, which is actually right. Because if it comes up with the right autocompletion, despite you having provided an incorrect variable name, that just refutes your hypothesis. That will then suggest that irrespective of what the variable name is, your autocompletion works fine, right? So then your loss function can then simply be to maximize the cross entropy between whatever is generated and whatever is the true sample or something of that sort, and then help the get to see if the algorithm goes ahead and finds new variable names. If the algorithm is not able to find new variable names, which maximizes the objective, then it kind of proves your hypothesis. Then it will prove the fact that variable names indeed do matter for the correct autocompletion to get generated. And if changing the variable name completely changes the autocompletion, then that establishes the causal nature of variable names for autocompletion. So that's like a broad idea of how to run like a causal kind of like an analysis in this kind of a setup. I hope that's not too high level and was like relatable enough to the code that we have discussed.